Alright, so in this video we're going to be determining the moment of inertia of a circular region, or a circular thin disk, and the region is going to be x squared plus y squared is equal to r squared, which is a circular disk with a radius of r. And we're going to be finding this moment of inertia about the origin, which is a perpendicular axis that runs through our region. But we're going to actually find the moment of inertia about the origin using our equation. The moment of inertia about the origin is equal to the moment of inertia about the x-axis plus the moment of inertia about the y-axis. Alrighty. And before we even get started, we're going to make a pretty simple simplification to find out the moment of inertia about the origin. We're going to say, alrighty, and keep in mind, we're going to say the density is still just equal to the density. But we're going to make a simplification to our moment of equation about the origin. Well, if you think about the symmetry of a circle, symmetrical about the x-axis is symmetrical about the y-axis, and it's also symmetrical about the origin. It is symmetrical from any line, or basically if you run a rod through the center of the mass and you rotate it, the function is never going to change. So we're symmetrical about the x-axis, the y-axis, and the origin, and it has a constant density, which we know from the region. So we can say that I of x, the moment of inertia about the x-axis, is equal to the moment of inertia about the y-axis. Alrighty. So this makes our moment of inertia about the origin equation equal to 2 times either the moment of the x-axis or the moment of the y-axis. We're going to choose the y-axis in this scenario. So the moment of inertia about the origin is equal to 2 times the moment of inertia about the y-axis. Alrighty, so if we want to find the moment of inertia about the y-axis, we first need to solve for the moment of inertia about the y-axis. So we have the equation of y is equal to the integral of x squared dm. And now we need to find both our region and also our dm. So we'll start by finding our little infinitely small slice of mass. So we know that dm is equal to dA times density. Density is just going to stay the same. But we need to figure out what dA is equal to. Well, let's go ahead and divide, or let's go ahead and make an example slice. So we have a distance of x, and then we have a little infinitely small piece of our region. And it has a width of dx, of course. But we need to figure out what our height of this region is. Well, we know it's going to be dependent on our functions, but currently we have the equation x squared plus y squared equals r squared. Well, we want to turn this function into a function of x, so we're going to solve for y. So we get y squared is equal to r squared minus x squared, and we have y is equal to plus or minus the square root of r squared minus x squared. And then by plugging in points, we know that our top little region, our region above the x-axis, is generated by the positive function of square root of r squared minus x squared. And the bottom region, the region below the x-axis, is represented by negative square root of r squared minus x squared. So the total length is actually going to be square root of r squared minus x squared minus negative square root of r squared minus x squared, which is equal to 2 times the square root of r squared minus x squared. So now that we have the little height of our region, and we have the width, we have dA is equal to 2 times square root of r squared minus x squared times dx. And then we can just insert dA into our density equation. So we have 2 times the density times square root of r squared minus x squared dx. Alrighty. So we can plug this into our moment equation. So we have I sub y. Moment inertia about the y-axis is equal to the integral from x squared times, then we'll bring our constants out, so 2 times the density, square root of r squared minus x squared dx. And then we can also go ahead and think about our bounds and plug in our bounds and make this a definite integral. If you think about the x values we're evaluating from, it's going to be from negative r to r, because our farthest left x value is going to be negative r, our farthest right value is going to be positive r. So we have negative r to r. Alrighty. Now that we have our bounds and we have our integral, we can actually go ahead and start integrating this thing. Well, the first thing we notice from this equation is actually going to be a difference of squares, which leads us to a trigonometric substitution. So we'll go ahead and draw our triangle. R squared is a positive value, so we know our hypotenuse is going to be r. X is going to be our negative value, so in this case, we'll go ahead and just make it our x value, and then we'll label theta. And then we know that because of the Pythagorean theorem, r squared minus x squared, the square root of it is going to be equal to our other length. So r squared minus x squared. So now we have our little triangle drawn out. So now we can go ahead and start thinking about our trig identities and how we can plug these in. Well, our first one that comes to mind, we'll go ahead and start with cosine of theta. Cosine of theta is equal to square root of r squared minus x squared over r. So r cosine of theta is equal to r squared minus x squared. Alrighty, that can be plugged in directly for our square root of r squared minus x squared. Now we can think of sine of theta. Sine of theta is going to be equal to x over r, which means that r sine of theta is equal to x. Alrighty. So now we can do two things with this. We can change our variable of integration, our variable that we're integrating with respect to, and we can also plug in for our x squared. So to plug in for our x squared, we're just going to square the whole entire expression. So r squared sine squared of theta is equal to x squared. So that gives us a value to plug in for x squared. But we can also think about a variable integration by taking the the derivative of both sides of the equation. So we have we have a constant, because r is a constant multiplied by sine of theta. Derivative of sine of theta is going to be cosine of theta. It's going to be multiplied by r, because r is constant. D theta is equal to, derivative of x is just dx. So r cosine of theta, d theta, is equal to dx. So now we can go ahead and plug in all three of these substitutions into our equation. So we have moment inertia about the y-axis is equal to We don't know our bounds for our integral yet, but we can solve for those here in just 1 second. For x squared, we have r squared sine squared theta. For square root of r squared minus x squared, we have r cosine of theta. And then for our dx, we have r cosine of theta d theta. Alrighty. And then we'll go ahead and find our bounds of integration. And we'll use this using r sine of theta is equal to x. Alrighty. So we can plug in our x values that we had for our original bounds. So r sine of theta is equal to r sine of theta is equal to negative r. Alrighty. For this, we're going to have theta is equal to pi over 2. Sine of pi over 2 is 1. 1 times r is positive r. Then for this one, we're going to have theta is equal to negative pi over 2. Sine of negative pi over 2 is negative 1. Negative 1 times r is equal to negative r. So those work for our bounds of integration. Negative pi over 2 pi over 2. And then we're going to combine like terms and go ahead and bring our r constants out. And then I'm sorry, in the last expression I forgot our 2 times density. That would be a fairly important part of our equation. So we have 2 times the density. And then now we can bring our r terms out. So we have r squared times r, which brings us to r to the 4th, times our integral from negative pi over 2 to pi halves of, we can combine our cosine terms, but we'll start off with sine squared theta times cosine squared theta. All this with respect to theta. Alrighty, and now we're going to have to use some Pythagorean, or we're going to have to first use a Pythagorean identity. And we'll use it on sine squared theta. Alrighty, so we have this expression is equal to 2 times your density times r to the 4th times integral from negative pi over 2 to pi over 2. And that is of 1 minus cosine squared theta times cosine squared theta, all d theta. We're going to go ahead and combine these like terms, so it's equal to 2 times density times r to the 4th times integral from negative pi over 2 to pi over 2 of cosine squared theta minus cosine to the 4th theta d theta. Alrighty, and now we're going to use our power reducing formula a couple times. So recall your power reducing formula for cosine. We have cosine of square root of theta is equal to 1 plus cosine of 2 theta all over 2. So cosine to the 4th of theta is going to be equal to this expression, squared, which is equal to cosine squared. Or sorry, we'll start off with our other value. So we have 1/4, our denominator value, is equal to cosine squared of 2 theta plus 2 cosine of 2 theta plus 1. Alrighty, and then we'll use our power reducing formula are one more time. So this is equal to 1/4 times, and we'll go ahead and separate our terms a little bit while using it. So to be cosine 4 theta over 2 plus 2 cosine 2 theta plus 1. Now 1 plus 1/2 is just equal to 3/2, so I'm going to go ahead and erase this one and put it in right there. Alrighty. Then that was meant to be a plus. And that was meant to be a plus. Alrighty, so now we have our expression for cosine to the 4th of theta. It is equal to minus we'll go ahead and apply our fractions. Cosine, or sorry, we'll have minus 3/8 plus cosine 4 theta over 8 plus cosine 2 theta all over 2. And we can have an in bracket. And then we'll go ahead and add our d theta on the end. Now we have our cosine squared of theta, which we can go ahead and also expand out to 1/2 plus cosine of 2 theta over 2. And then we can add our constants out front. Alrighty. And then now we can go ahead and combine our like terms. So we have 1/2 minus 3/8 1/2 minus 3/8, which is 4/8 minus 3/8, is equal to 1/8. And then cosine of 2 theta over 2 minus cosine of 2 theta over 2, those terms cancel out. Then we'll mark off these. Then we have minus cosine 4 theta over 8. We have all that d theta. Alrighty. So we'll go ahead and we will go ahead and integrate one part of our problem with just respect to regular theta. So we have 1/8, which can just be theta over 8, evaluated from negative pi over 2 to pi over 2. That's multiplied by 2 times density times r to the 4th. We'll have a larger fraction. This is minus our integral cosine 4 theta over 8 d theta. So negative pi over 2 to pi over 2. Well, for this, we're going to have u is equal to 4 theta. Du is equal to 4. d theta. So du over 4 is equal to d theta. So we have cosine, and I'm just going to write this little part of the expression out. So negative cosine of u times the fourth, so over 32. And then we can reevaluate around. So u is equal to 4 times theta. So pi over 2 times 4 is going to be equal to 2 pi. And then negative pi over 2 times 4 is going to be negative 2 pi. And then that's going to be with respect to u. So now we have our total expression, which is 2 times integral, or 2 times our density times r to the fourth times theta over 8, evaluated from theta is equal to negative pi over 2, 2 pi over 2. Minus and then we have cosine of u, intercosine of u is sine of u over 32, evaluated from 2 pi to negative 2 pi. Alrighty. So now we have 2 times our density times r to the fourth times pi halves over 8, which is pi over 16, minus, and now we have negative pi over 16. Now we subtract this expression. But we know that sine of 2 pi is going to be 0. Sine of negative 2 pi is also going to be 0. So that's going to be minus a big 0 because it doesn't matter that it's divided by 32. So this leaves us at the expression 2 times the density of r to the fourth times pi over 8. Alrighty. So now if we do a little bit of simplification, we get our density times r to the fourth pi over 4 is equal to our moment of inertia about the y-axis. So the moment of inertia about the origin is equal to 2 times the moment of inertia about the y-axis, which is equal to density times r to the fourth times pi over 2. Alrighty. So that is going to be our moment of inertia about the origin for a general circle, depending on what your r value is. But we can also go one step further and say that, all right, density of a circle is going to be equal to pi r squared, or mass over pi r squared. And whenever we plug that into our equation, we get the moment of inertia about the origin is equal to mass over pi r squared times r to the fourth pi all over 2, which is also equal to mass times r squared over 2, which is our more general form for the moment of inertia of a circular disk about the origin. So thank you all for watching.